Algebra 2 Honors, 3.1, some supporting skills. We're going to do this lesson before we get into the first section in Chapter 3. And we are simplifying radicals, finding differences of squares and perfect square trinomials, using factoring to solve, and using the quadratic formula to solve. So first of all, simplifying radicals. You're going to not have access to a calculator. You need to be able to do these by hand. And so I'm going to show you what I call the ladder method, because what we want to do is find the largest perfect square that goes into the number. So number one, what's the largest perfect square that goes into 48? And you might know it and you might not, especially when the numbers get bigger. And in the ladder method, we are going to prime factor. And if we do our prime factoring correctly, we won't have to worry if we don't find the biggest perfect square that goes into it. So prime numbers are 2, 3, 5, 7, 11, 13, etc., etc. And so what I'm going to do is I'm going to start with 2, the smallest, and I'm going to divide 2 into 48. And it goes into 4 twice, and it goes into 8 4 times. So I'm just doing longhand division. And then that 24 is also divisible by 2, so I'm going to take 2 into it again. I'm going to keep on using 2 until it doesn't go into the number anymore, and then I would switch to 3, then 5, then 7, then 11 as necessary. And so 2 goes into 24, and it leaves you, as it goes in, you have 12. It goes in there 12 times. 12 is even, so 2 goes into 12, and 12 divided by 2 is 6. And then 6 is even, so 2 goes in again, and 2, it goes in there 3 times. And we're done because this last number is prime. So the prime factorization of the square root of 48 is 2 times 2 times 2 times 2 times 3. If you multiply all those out, you will have 48. And then what we're going to do is every pair creates a perfect square. So I can make this as the square root of 4 times the second pair produces a square root of 4. And then lastly, the square root of 3 is just by itself, so it's just underneath the radical as square root of 3. And the square root of 4 is 2. The square root of 4 is 2 times the square root of 3, and we have 4 square roots of 3. And we have simplified the square root of 48. Now, the other method, if you know that the square root of 48, the largest perfect square is 16, and it's 16 times 3, then that's the square root of 16 times the square root of 3, and you can get 4 root 3 that way. And that's fine. That's a great method when the numbers are smaller, but when the numbers get larger, it's kind of hard to know what the largest perfect square is. So the ladder method kind of can be helpful. All right, let's look at number 2. When we have a fraction, we can break that up into the square root of the numerator over the square root of the denominator. Unless they simplify, we could simplify the fraction if that's the case. And then the square root of 49 is kind of nice because the square root of 49 is just 7. But the square root of 252, you might not know the largest perfect square that goes into that. That's why I'm going to use prime factorization. And there is something that's kind of nice. If I add up the digits, 2 plus 5 plus 2 for 252, I get 9. And since 9 is divisible by 3, 252 is divisible by 3. So somewhere along the line, we're going to be using 3 as we divide into it. And we could start with that. We can also start, since it's even, with dividing by 2, and it goes into 2 once, into 5 twice, with the remainder of 1. It goes into 12 6 times. So I'm just doing longhand division. In my head, half of 252 is 126. Then we're going to put 2 in there again. Half of 126 is 63. And 63 is no longer even, but if I add up the digits, 6 plus 3 is 9. It is divisible by 3. 3 goes into 6 2 times. 3 goes into 3 once. And then 21 is divisible by 3. It is 3 times 7. 7 is prime, so I am done prime factoring that. And so what I'm going to do, what always happens, is that for every pair, I get a perfect square. So note in this first one, 2 times 2 is a square root of 4, which just creates 2. The other 2 times 2 created the square root of 4, which gave me 2. So I know that this 2 times 2 is a square root of 4. It's just going to be a 2 on the outside. This set of 3's is a square root of 9. It's just going to be a 3 outside. The 7 has to remain under the radical because it wasn't paired up with anything, and it's not a perfect square. And so when I multiply, I get 6 root 7 all over 7. Those 7's do not simplify. There's nothing more to do with that. And there that is in simplified radical form. In number 3, I'm going to break it up into the square root of 50 over the square root of 3. And with 50, if you happen to notice that, there we go again. So on 50, if you happen to know that the square root of 50 is 25 times 2, therefore it's 5 square roots of 2, you can do it that way, no problem. Or you can do that ladder method where it's even, so 2 goes into there 25 times, and then 25, 5 is the prime number that goes into there. It's 5 times 5. And there is a pair of 5's, and for that pair, we put 1 outside, and we have a singleton, that's a 2, so that stays under the radical. And this is all over the square root of 3. Now, the only thing is when we say simplify, we don't let radicals remain in the denominator. And so we have a process that's called rationalize the denominator. It just means I don't want anything with a radical in the denominator. So what we do is we multiply by whatever that radical value is in the denominator, both top and bottom. So if I multiply by root 3 over root 3, I'm really multiplying by 1, and I won't change the value. And so when I multiply the denominators, root 3 times root 3 is 3. In the numerator, when you multiply the root 2 and the root 3, you multiply the numbers underneath, and you get root 6. And of course, we still have all of that times 5. And there we have simplified the radical. We do not leave radicals in the denominator. We do this process that we call rationalize the denominator. So there's simplifying radicals. Then we have factoring differences of squares. And so this is the formula. When you have two numbers that are perfect squares and they are being subtracted, it factors into the quantity a plus b times the quantity a minus b. And so in number 4, 16x squared is a perfect square. 25 is a perfect square. And so it factors into that square root of 16x squared. The 4x will be in the beginning in both quantities. That's that you have a squared, so a starts off both quantities. And then 25 is a perfect square. The square root of it is 5. That's going to end it. And one of them is positive and one of them is negative. You always want to make sure that there isn't any further thing to take out, and there isn't, so that's good. Caution on this, because sometimes people see perfect squares, but it's addition and think they can factor it. It doesn't. It does not factor over the reals. It must be a difference of squares. Okay, the next ones could be a little tricky because 4 and 256 are perfect squares. 256 is 16 squared, but there's really a common monomial factor that we can take out first. 4 happens to be a factor of 256. And if I take 256, divide it by 4, I get 64. Now notice as I drop down, I started with an equals. that 4 has to be part of my answer because I want an equivalent expression to the one I started with. The 4 doesn't disappear, it just needs to be there on the outside. And then after that, a squared is a perfect square, 64b squared is a perfect square. So we're going to start both quantities with a, and the square root of 64b squared is 8b. So we're going to end both quantities with 8b. And one is positive and one is negative. And then when you box your answer, don't forget that 4 is part of it. Factoring perfect square trinomials. Well, we've gone from the square of a binomial is a trinomial, square it, multiply, and double it. Now we are just going from the trinomial back to the square of a binomial. And what you need to notice is that the first term and the last term are perfect squares. If that's the case, you want to check out if I take 2 times the square root of that first number and the square root of the last number, noting that x squared and 169 are perfect squares. 13 squared is 169. You want to make a list of perfect squares up to 25 and be familiar with them so that you can go, oh, 169, that's 13 squared. Well, if I see the beginning and the end starts with perfect squares, I am going to take their square roots and double them. And if that is the absolute value of the middle term, this is a perfect square trinomial. And it simply factors into, since the middle term's negative, this is going to be subtraction. When it's a squared minus 2ab, it factors into a minus b. And the square root of the first term, the square root of the last term are what we are using in that binomial. So the square root of the first term is x, and the square root of the last term is 13. And that should be the factorization of that perfect square trinomial. If you check your work by square it, and multiply and double it, so if I expand it using that special property to expand a binomial, I can check to see that, yep, it does expand back to what we started with. But the answer is this factored form. Below was just to check to see if I did it right. All right, so in number 7, by the way, I had originally, and so you probably don't have the correct, or you probably have the original problem, as I ran them off before I realized I didn't have the correct problem in here. So it was originally 36x squared plus 124x plus 625. I have replaced it. Please replace it with 16n squared plus 24n plus 9. And so when I look at this, I go, oh, 16n squared, that's a perfect square. 9 is a perfect square. So I'm going to check to see if this is a perfect square trinomial. So I'm going to take 2 times the square root of 16n squared times the square root of 9. And I get 2 times 4n times 3. And that is 24n. And so that is the absolute value of the middle term. So this is a perfect square trinomial. And so it factors in, since this middle term is positive, it's going to be addition. And it is simply the square root of this number in front and the square root of 9 in the back. And that is your factorization of the perfect square trinomial. Again, you can check, square the 4n, square the 3, and that's always positive. And if I multiply 12 and double, I get 24n. So if I expand, square it, multiply, and double it, it does check. Make sure, though, that your check doesn't look like your answer. Your answer needs to be boxed. Your answer is the quantity 4n plus 3 squared. So we've done some simplifying radicals, some factoring. Now we are going to solve by factoring. And so we have an equation. We are looking for the values of x that make this 0. And so we are going to factor the x squared minus x minus 12. I need numbers that multiply to be negative 12, such as negative 3 and 4, or a positive 3 and a negative 4, or 2 and a negative 6, or a negative 2 and a positive 6, or 1 and a negative 12, or a negative 1 and 12. And I need the ones that, since it's a 1x squared, it's a little easier. Which of those add up to a negative 1? The coefficient of x, the 3 and 4, so that tells me this factors x plus 3, x minus 4. And that equals 0. Don't forget the equals 0 on that. And then if two things multiplied are 0, one or the other must equal 0. So either x plus 3 equals 0 or x minus 4 equals 0. So as we solve, we get x equals negative 3 or x equals 4. And those are my solutions. You could go back and plug them in and see if they work. Now, on this next one, factoring, I'm a firm believer in trial and error. And it is important that it's equal to 0. If it's not, set it equal to 0 before you get started. And to get a 2x squared, I really have only one combination, 2x and x. But now to get a negative 15, a 3 and a negative 5, or a negative 3 and 5, or a 1 and a negative 15, or a negative 1 and 15. My experience is that the ones that are closer together are used more often, and that's what I start with. But if they don't work, then I'm going to use the other. And then I am putting them in place, and I am purposely choosing one that's not going to work. And what we do is we check the outer product is 6x, and the inner product is a minus 5x. Does that add up to a negative 7x? Nope. So that means I've got to go back to the drawing board. And what if I switched? I made this 3 and made this 5. Then 2 times 5 is my 10x, and negative 3 times x is a minus 3x. It's a positive 7x, and that's good news. Even though it's not a negative 7x, all I have to do is switch the signs and make it a positive 3 and a negative 5. Then this would be a negative 10 and a positive 3, and those add up to negative 7x. So that means I have factored this correctly. So basically you have to multiply it out to see if it's correct. So then from there, we're just going to say 2x plus 3 equals 0, or x minus 5 equals 0. We get 2x equals a negative 3, divide by 2. X is a negative 3 halves, or add the 5, x is 5. Now, there are some other ways of factoring, and so you need to go back and practice whatever method you learned, and you are expected to be able to factor whether the coefficient of x squared is 1 or something else. So you might need some practice with that. You might need to look up some more videos on that. All right, solve by using the quadratic formula. So to solve ax squared plus bx plus c equals 0, note it's equal to 0. That's important. It must be equal to 0. We use the quadratic formula, and we have to use these values of a, b, and c to solve for the values of x that make this 0. So in number 10, it's set equal to 0. My a value is 2, my b value is 3, and my c value is negative 20. It says solve by using the quadratic formula. And by the way, you need to memorize that. It's not given. You actually need to know it. So anyways, we get x is the opposite of b, so negative 3, plus or minus the square root of b squared, so 3 squared is 9, minus 4 times a times c. And I needed to extend that radical. You should do the same thing if yours isn't long enough. And then it's all over 2 times the value of a. So all over 2a. Then do the math. And underneath here, 8 times 20 is 160 plus 9. is 169, and that is all over 4. And the square root of 169 is 13, and we get x is a negative 3 plus 13 over 4, or x is a negative 3 minus 13 all over 4. And so x is 10 fourths, or x is a negative 16 fourths. No calculator. You need to be able to just simplify these. So 5 halves, or x is a negative 4. And those are my solutions. All right, and number 11, note it is not equal to 0. So the first thing you need to do is set it equal to 0. Add 10 to both sides, and we have a minus 3 equals 0. Now it's A is 2, B is negative 7, and C is negative 3. So in this case, it's not x, it's m. So we get m equals, the opposite of b is 7, plus or minus the square root of b squared, which is a positive 49, minus 4 times a times c. And if your radical is not long enough, extend it. And then all over 2 times a. And we have 7 plus or minus the square root of, we got a negative 4, negative 3, it'll be positive. 12 times 2 is 24. 24 and 49 is 73. And 73 is prime. There's nothing, if I add the digits, 7 plus 3 is 10. There isn't anything that, there are not two integers that multiply to be 73. So my answers are 7 plus the square root of 73 over 4, or m is 7 minus the square root of 73 all over 4. If that underneath the radical can be simplified, then I refer you to the first 3 examples. You need to simplify the radical. That's it.